So perhaps now we're asking ourselves, could we build a fusion reactor using a linear or an open configuration of magnetic field? Well, let's imagine we tried this simple one together. Let's take some magnets, which we'll call field coils. They're just going to be electromagnets that we're going to run a current in, and then that will produce a magnetic field that is running down through the center of the magnetic field coils. So a charged particle is allowed to stream very quickly along these magnetic field lines. And based on the parallel speed that we'll calculate together for these particles and the notes, you'll find that if you have fusion relevant temperatures of 15 kiloelectron volts, a linear device like this would have to be thousands and thousands of kilometers long in order to keep a fusion plasma hot enough and dense enough for a long enough period of time to get net energy out. This becomes really impractical. So we can't build a linear device the size of the Earth or the size of a country, basically. We've got to get much smarter. So now that you're already thinking about how magnetic fields can hold and confine charged particles, maybe in your head you're coming up with all sorts of interesting ways of bending and twisting and molding those magnetic fields into some interesting configuration, because you've got to plug up the ends. You've got to keep these particles from just free streaming out the ends. And so maybe you've already drawn on a piece of paper or thought about some different options for how you'd wrap the magnetic field around to confine the particles. If you've done that, you're not alone. Fusion researchers have been studying these kinds of different options for many, many decades. Just a few examples are shown here that we'll go over more in the notes: a field reverse configuration, a spheromac, a magnetic mirror, a cusp. There are dozens of these types of configurations where people are trying to find ways of plugging up those holes and keeping the particles confined in a more compact device that's not thousands of kilometers in size, trying to hold that plasma for a long enough time to make fusion actually worthwhile. So one problem with just bending and twisting the magnetic field lines into any configuration we'd like is we can actually show mathematically that once you start doing this, and once you start adding any kind of electric field to the system, there are new particle drifts, new particle motions that arise. And these particle motions, unfortunately, tend to conspire to spoil any confinement properties that we're sort of looking at. So let's go through a couple of these different drifts together. We'll talk about the E cross B drift, the grad B drift, and the curvature drift. First, let's talk about the E cross B drift. So we've shown ourselves the picture of our standard situation where we have a magnetic field coming out of the board and we have ions and electrons gyrating about that magnetic field. Now let's look at the situation where we introduce a transverse or perpendicular electric field, perpendicular meaning perpendicular with respect to the magnetic field line direction. So if magnetic field is coming out of the page and the electric field is going up on the page, what this will actually lead to will be an E cross B drift, which will move the particle to the right. And if we look at this for an electron, we'll find that the particle moves again to the right. So in the presence of a magnetic field and electric field that are at right angles to each other, particles will drift in the E cross B direction. And this drift will occur regardless of the mass of the particles and regardless of the charge of the particles. So we'd have to be very careful if we introduced any electric fields in our system that we understood where this E cross B drift was pointing, so we understood how this drift might be leading to any particle losses. Let's look now at the grad B drift. This one is interesting because unlike the E cross B drift, it's going to cause the ions and the electrons to move in different directions, meaning the ions and the electrons will separate. When this charge separation happens, we create an electric field. So we better be careful if we introduce a gradient in the strength of the magnetic field anywhere in our system. For example, if we tried to pinch the field lines together at the end of a mirror machine, we're creating stronger magnetic fields at the ends than in the middle. And that means that we'll have a gradient in the magnetic field along the device, and that would lead to a grad B drift. And so in the situation where we have a magnetic field that varies with strength, if we have a strong magnetic field at one part of the gyro orbit, versus a weak magnetic field at another part of the gyro orbit, what actually will happen is the particle's orbit will become distorted. And that distortion actually leads to the particle getting a little bit of a squeezed orbit on one side, where the magnetic field is strong, and a more unsqueezed or larger orbit where the magnetic field is weak. This distortion of the orbit leads to a drift going into the left in this case. So if our gradient in B was pointing up, the direction of the magnetic field was pointing out at you, then you would end up getting a drift to the left. That would be for the ions. And now if we look at the case for the electrons, with exactly the same direction of the magnetic field and the direction of the gradient in the magnetic field, you would end up getting a drift of the electrons going to the right. So in the presence of a gradient in the magnetic field, particles drift in the Q, that's charge of the particle, times the B direction crossed with the grad B direction. And so this is a direction which is perpendicular both to the magnetic field and the gradient of the magnetic field, but unfortunately it's not in the same direction for both electrons and ions. They move in opposite directions, as you can see, and this can produce an electric field. And once we've produced the electric field from charge separation, now we have to contend with that very first drift we talked about, the E cross B drift. So we're going to have to be a little careful if we create a gradient in the strength of our magnetic field while we're bending and twisting these field lines trying to get good confinement. The last particle drift we want to talk about is the curvature drift. Now this curvature drift is also going to cause ions and electrons to separate and will also create an electric field. This drift is sort of a little easier to think about because if we have a curved magnetic field, so we've come and we've bent our magnetic field in our configuration, now any particle that is following that field line that's curved is going to actually feel a centrifugal force. This centrifugal force is going to have the effect of providing the particle with a little kick, a little bit of a new force in one section of its orbit, and a little bit of a pull, right? A sort of absence of force on the other section of its orbit. And so again, you'll get a distortion in the gyro orbit of the particle, which will lead to the curvature drift. And so if we imagine that our magnetic field is coming out of the page, and we have a centrifugal force which is pointing up, for the ions we'll get a drift, which is the curvature drift, which is going to the left, and for the electrons we'll get a drift which is going to the right. The overall drift, if you calculate the cross product, is going to be the charge of the particle Q times the radius of curvature crossed with the magnetic field direction. So just like you've been imagining, well, I think I could bend and twist these magnetic field lines into some kind of great configuration to plug up the N losses. Again, people have been looking at this for a very long time. Many linear or open magnetic confinement configurations have been studied and in fact continue to be studied up to this day as folks are trying to optimize what kind of plugs they can use to stop the N losses. In fact, the two pictures that I'm showing you here are from very recent announcements about improved sort of magnetic configurations that are open. The first one is from a private company called Tri-Alpha Energy, located in Southern California. You can see a picture of their linear device here and a little person standing next to it. And below that is a picture of another open magnetic confinement configuration proposed by Lockheed Martin. So these configurations and others tend to be combinations of more canonical configurations that we'll show you in the notes, called a theta pinch, a Z pinch, a cusp machine, a field reverse configuration or FRC, mirror machines, a plasma focus, a reverse field pinch, a screw pinch, or a tandem mirror. So if you see any of these names, those are all names that you should now associate with options for magnetic confinement.